Uh-oh. Okay, thermochemistry. My apologies for my absence. Please don't be too upset with me. I'm going to give you guys your practice test before break, or Georgiadis will give you your practice test. Please go ahead and finish your practice test before you get back. That way you have the full period on Monday to ask me questions. Be prepared to work the questions when we come back, and I will answer any questions that you guys email me while I'm gone. Okay. So the first thing we're going to talk about is, or at least in chapter 6, and then following, I think, in chapter 17, is energy. We're going to discuss energy in terms of chemical potential energy and how it changes from one form to another to accomplish work. We're going to focus specifically on energy transfers. It's important that you guys understand that while the energy in the universe is constant, that does not mean that everything is 100%. So you're not going to get 100% yield. You may get something that's less, but the energy is just lost as heat. So the definition, of course, energy, the capacity to do work or produce heat. Work is going to be, at least in terms of physics, defined specifically as the force acting over a distance. But in our case, it's going to be a little bit different. But it is going to involve a transfer of energy from one substance to another, or from one chemical compound to another. So anyway, the first law of thermodynamics states that, let's see, get it to come up here, that energy can be converted from one form to another, but you're not going to lose any energy, so it's neither created nor destroyed. The total amount of energy in the system, or in the energy, or in the universe rather, is going to stay the same, like I said. Some energy could be lost, but the energy would just be lost as heat. The total amount of energy still stays the same. So I don't want you guys to freak out. Seeing the equations here, I know I've had some students that see the equations, immediately think of physics and want to run out of the room. I don't want that to be the case. But we are going to talk about potential energy and kinetic energy, and there are formulas associated with both. So your kinetic energy formula is going to be 1/2 mv squared. We're not going to give you velocities to calculate kinetic energy. We're going to do a little bit differently, but that's all right. Potential energy is mass times gravity times the height. But then again, we're not going to use the formulas necessarily from physics to calculate your potential energy. The units for both energy, all of it's going to be joules or kilojoules. Most of the ones we use will end up with joules, but we'll do conversions to kilojoules to use them in our formulas. The kinetic energy, of course, is the energy of motion, and potential energy, the energy of position. Not something new for most of you. Okay, so heat. If you take your hand and grab the metal portion of your chair, or the metal part of your chair, of course, if you're doing this at home, you might actually be in a softer chair, but anyway, if you touch that, it feels cold. That means that the energy is actually leaving your body or leaving your hand and going into that other substance. That substance, therefore, has a lower specific heat than you do, and so the energy is lost to you. So that's a heat or energy transfer. So that's the way we're going to talk about these things, is transfer of energy from one substance to another. It's always going to move. The heat is from the warmer object to the colder object, from the object that has necessarily usually the higher specific heat to one with a lower specific heat. The temperature is basically a measurement of the average kinetic energy of a substance. As defined here, it's a property that reflects random motions of the particles of that substance. Now, there's two ways we're going to see this graphically. One is in terms of an exothermic and the other an endothermic reaction. You guys have drawn these graphs in pre-AP and should be familiar with it. But there's a graph here on the bottom right, but your endothermic reactions, the product will end up higher, and for your exothermic reactions, it's going to end up lower. So your exothermic reactions are going to end up below the starting point in terms of the amount of energy in the system. Okay. So there's a graph for the endothermic. I'm sorry. The energy is going to actually flow into the system. So these objects will actually feel colder to the touch. So like a cold pack, when you activate the cold pack, the ammonium nitrate, it's actually going to absorb energy from the system in order to ionize those products, and so or ionize those reactants. And so you'll end up with something that actually has more energy than what it started with, and so it removes energy from the system. Okay, so here, when we talk about our chemical reactions, and I know this seems very simple, but we say that the actual reaction is your system, and everything that surrounds that system is considered the universe or the surroundings. So in terms of our reactions, if it's done, of course, in a closed system, we call that inside that closed system the system or the reaction. And then everything outside that flask is considered the surroundings, which is technically, I guess, the universe, of course, encompasses all of it, but the surroundings would be everything outside that reaction. To calculate internal energy of a system, and I know you guys are going to say, Mr. Tall, this is so easy. I agree, it is day one, but these equations are very simple to calculate. So the change in energy of a system is going to be the amount of work plus the amount of heat that is actually released. So, and the sum of that is going to be the total energy. Generally, it's in joules, but it could also be in kilojoules. So in this case, for delta E equals Q plus W, Q is going to be your heat, and then W is going to represent your work. There is a separate calculation for work. I believe it's on the next slide. But you will calculate work in terms of a difference in force over a particular distance. So your endothermic reactions are going to have negative values for your energy, or negative Q values, and your endothermic reactions are going to have positive values, and you guys are aware of this. So let's do an example. If the delta E, to calculate the change in energy, if Q is negative 50 and the amount of work is 35 kilojoules, the units are the same, so you're just going to add these two together, you'll end up with a change in energy that is negative. So this would be, in fact, exothermic. Simple. Work on gases, this is where we'll actually do work calculations. The definition for work is going to be a change in, well, actually, work is force times distance. For us, the work is not going to be really force. We're going to use pressure as a measurement of that force, and the distance is going to be the change in volume over a particular period. So you'll look and usually do a subtraction to find your volume, and then your pressure values will be given to you. So an example, and again, these are pretty simple. Calculate the work if the volume of a gas is increased from 15 mils to 2 liters. Make sure your units stay the same, and they don't here, at a constant pressure of 1.5 atmospheres. So if I calculate, I just do a subtraction to find out the volume. So 2,000 milliliters minus 15 is going to give me 1,985 mils, or 1.985 liters, times 1.5 atmospheres, and then make sure you use the negative value for your pressure. And you end up getting negative 3 liter atmospheres. The units for pressure in this or in this section are going to be liter atmospheres, okay, instead of joules. Joule, liter atmosphere, they're the same, but right liter atmosphere, you make sure your units are the same. And I think we're going to stop there for the first day, if memory serves. And it does. We're going to stop at work on gases, and we'll pick up enthalpy and calorimetry tomorrow. Okay? I miss you.